In this video, we will talk about complexity curves and feature curves. First, let us start with why we may want to use these curves. Okay, these curves can give you several insights. For example, are we overfitting or are we underfitting? If you know this will give you some hints on how to improve your model. Using these curves, we will also see how the optimal complexity depends on the training set size. Finally, we will discuss how to tune the complexity and the number of features using these curves. On this slide, we see several regression models on the left. Note their colors: orange, blue and green. On the right-hand side, we see the complexity curve. In a complexity curve, the flexibility or complexity is on the x-axis. In this case, we use the polynomial degree as an indicator of flexibility. On the y-axis, we have the performance in terms of the mean squared error. We see two lines, one for the train error and one for the test error. Now regarding these curves, you see there are colored squares in the right plot. They correspond with the regression models in the left-hand plot. The orange line on the left, for example, corresponds with the two orange squares on the left in the complexity plot. Okay, now let's talk about this orange model. This orange model is underfitting. This can be seen because it has a high train and test error. It has a high bias and a low variance. This model is too simple or not flexible enough. So in the left part of the complexity curve, we have underfitting, where the least complex models are. The green squares in the right of the complexity plot correspond to the wiggly green regression model on the left. This model is overfitting. This can be seen by the fact that its test error is high and its train error is low. This means the model is too flexible. This will be in the right part of the complexity curve, where the most complex models are. Now let's discuss some of the trends that we observe. We see that if we increase the flexibility, the training error, the gray line, decreases. This is in line with our expectations. The more complex your model, the better it can fit the training data. Therefore, the training error goes down. On the other hand, for the test error, the red line, we see a U-shape. This U-shape is also the typical shape that we expect to see. Why? Well, this is a difficult question. If you cannot get it, don't worry about it. You can understand this through the bias variance decomposition. Please pause the video and think about it. Afterward, we discuss the answer together. Okay, welcome back. Let us discuss the answer. Remember that the bias variance decomposition decomposes the error in three components: the bias, the variance, and the irreducible error, epsilon. For this analysis, we're going to ignore the irreducible error epsilon. Anyway, it is a constant no matter what flexibility we choose. Okay, we have the more flexible our model, the smaller the bias. Because we are more flexible, our errors due to approximations get smaller, and therefore the bias gets smaller. The variance behaves just the other way around. The more flexible our model, the larger the variance. Because the bias and variance are summed together, we obtain this U-shape. Now I have a question for you. If we increase the flexibility of our model, does this lead to a better test performance? Please pause the video, think about it, and afterward we discuss the answer. Okay, welcome back. It seems we can reason into two directions. On one hand, more flexibility reduces the bias. Therefore, we have less underfitting and thus the performance should improve. On the other hand, we can reason that more flexibility leads to a higher variance and thus to more overfitting. Thus the performance should get worse. Now, which is it? Well, the answer is it depends on where you are in this complexity curve. If we are in the underfitting regime, on the left, our bias is dominating the error. Then we should try and lower the bias as much as possible. Thus, if we are underfitting, we should increase flexibility. If we are in the overfitting regime on the right, the variance is very large. In that case, we should try to decrease flexibility to reduce this variance. Thus, if we are overfitting, we should decrease the flexibility. Okay, so now what is the conclusion? Well, the conclusion is flexibility is a hyperparameter. As such, you should tune it on some test data. You can make the complexity curve to gain some insight into your situation, so you can figure out if you are overfitting or underfitting. Now let us have a look at the complexity curve if we vary the amount of training data. Here we have three complexity curves. One curve where training is done with 10 samples, another curve where training is done with 50 samples, and the third curve uses 100 training samples. I have indicated the optimal complexity with a red square. Observe that the bigger the training set, the larger the optimal complexity. In fact, the whole complexity curve seems to move to the right. Why is this the case? Well, the more complex our model, the lower the bias, but the higher the variance. However, what happens if we increase the amount of training data? If we increase the amount of training data, the variance is reduced. So the effect of the increased variance can be compensated. The bias remains constant if the amount of data is increased. This results in a lower total error for a higher complexity if you have a larger training set. The conclusion is, if we get more training data, we should increase the complexity of our model to get a better performance. A second conclusion is that if you are tuning the complexity parameter using test data, you should do the tuning again if the size of your training set changes, because the optimal setting of the complexity parameter is sensitive to the size of the training set. Now we have discussed everything regarding the complexity curve. Let us now talk about the feature curve. A feature curve is obtained by varying the amount of features and plotting the train and test error, or here we use the mean squared error. Okay, now it is important to recall the concept of garbage features. Features that are pure noise and not useful for the task at hand. My question to you is, what happens if we add features that are pure garbage? What will happen with the test mean squared error? You can figure this out by considering the bias variance decomposition. Please pause the video and afterward we discuss the answer together. Okay, welcome back. With pure garbage features, we will see that the performance will strictly get worse. Why? Well, the bias stays the same because the features are not informative for our task. We will, however, get an increase in variance because the model may overfit to the added noise. Therefore, the whole test error must increase. Okay, now let us assume that the features are not garbage, meaning the features are actually useful for the prediction task. Now keep in mind, the more features we have, the higher the dimensionality and therefore the more parameters we have. Thus, this means if we have more features, essentially our model is more complex. Now my question to you is, do more features improve the test error? Please pause the video, think about the answer, and afterward we discuss it together. Okay, welcome back. The answer is, it depends. More features mean a more complex model. Therefore, the feature curve and the complexity curve are very similar. Again, there will be a U-shape for the test error, also for the feature curve. This means that more features don't always help. It depends on where you are in the feature curve. If you are in the left part of the feature curve, where we are underfitting, more features will improve performance. If you're on the right side, where we are overfitting, less features will improve performance. Just like the complexity, we can see the number of features as a hyperparameter. We can tune it on test data to get optimal performance. If you want to get insight into whether you are overfitting or underfitting, you can make a feature curve. We can also have a look at the feature curve when we vary the amount of training data. Let us again assume that there are no garbage features. In that case, we will also observe that the optimal number of features increases the larger the training set size. Why is that the case? Well, the argument is almost the same as for the complexity curve. Let's see if you can reproduce this argument. Please take a moment to think about this, pause the video, and afterward we discuss the answer. Okay, welcome back. Let's discuss the answer. The more features you have, the lower your bias, but the higher your variance. But this higher variance is compensated. The variance is decreased because we have more training data. Furthermore, the bias remains constant when the amount of training data changes. Therefore, the total error will be lower. So what are the conclusions? If we have more training data, it is better to use more features. Then we can also get a better performance. Also, if you get more training data, you should redo the tuning of the amount of features, as the optimal amount of features will change depending on the size of the training set. Okay, let's summarize this video. We have discussed the complexity curve and the feature curve. We have explained that the test error will have a U-shape for both curves. Using the bias variance decomposition, we could understand this behavior. Furthermore, we discussed in which part of the curves we are overfitting and underfitting. We talked about whether an increase in flexibility or number of features always results in better performance. The answer is, it depends on where you are in the feature or complexity curve. Finally, we discussed that complexity and the number of features are hyperparameters that need to be tuned. They should be tuned on test data. To get more insight into what is happening, you can make a complexity curve and feature curve. They will tell you whether you are overfitting or underfitting and how to improve your model. Finally, we saw that if we get more training data, the optimal complexity increases and the optimal number of features also increases. Therefore, if the amount of training data changes, we should retune these hyperparameters.